We're going to continue on how to simplify some radical expressions. Now, really, this simplification works on just one principle. It's just one little principle, and you guys have seen this for a long time. In fact, you've simplified radicals before. We're just going to make them, of course, a little bit more advanced for this class. Simplifying radicals works on one little rule. It's called the product rule for radicals. And here it is. It says, if you have a square root of a times b, a square root can be broken up. The product can be broken up. For instance, if I have the square root of a times b, that comes down to the square root of a times the square root of b. In fact, I showed you that before. In fact, I've previewed this section before in section 10.1. I kind of told you what we're going to do already in this section. But this lets you solve or simplify a lot of these radicals. I'm going to put this a little bit, well, I'll give you an example first to prove that it's true by one example. Then I'll make this in general for you. So here's a little quasi-proof. If I have the square root of 36, I know the square root of 36 is, well, that's 9 times 4, right? You follow me?
Mm-hmm.
According to this product rule, I should be able to separate the square root of 9 times the square root of 4. How much is the square root of 9?
3.
How much is the square root of 4?
2.
And that is equal to,
6.
how much is the square root of 36? It does work. Okay, so if we can break up some number or some quantity as a product, I can split that radical up, do each of the radicals individually, and multiply their results, so those products, and that will give me the same answer as if I would have done it normally. Are you following this? Now, not only does this work for square roots, this works for any type of root. Just don't forget the n. A lot of people lose the n. Whatever that power is, or whatever that root is, you got to keep that root. Also, I need you to know that this works both ways here. If I have the square root of 2 times the square root of 7, can I multiply those roots together? Well, that's what this says as well. It says if I have an nth root times an nth root, I can put them under the same nth root. Does that make sense?
Mm-hmm.
Okay, so let's try it. If I have a square root of 2 times a square root of 7, what type of root am I going to get?
Square root of 13.
Still a square root. Sure, it says the same root, doesn't it? Same root. Square, and then what do I do with the 2 and the 7?
2 times
2
7.
times 7.
So that's a square root of 14. That works. We can put some roots together as well. How about that one? Are these roots able to be put together? Can we put those things under the same root?
Yep.
Yes.
What lets you know that?
If the root's the same.
Okay, so let me ask you a question. If I had this, could I do it?
No.
No, that's not what this says. This says the ends have to be the same. So what we're looking for when we're combining our roots, we're looking to see if we first have the same root, and then we're going to multiply the radicands, whatever's inside them. So what type of root are we going to have, ladies and gentlemen?
4th root.
4th root of?
6 times 3x squared.
Good. How much is 6 times 3x squared?
18x squared.
Okay.
25.
Is there anything I can do to simplify that the rest of the way down?
No.
Let's see. Can you think of a fourth root that divides 18? Can you think of that?
No.
I can think of a square root. I can think of, perfect square. I think of 9, but that you can't find the fourth root of 9. Find the square root of 9. We're doing the fourth root. We'll deal with how to simplify that in just a little bit. Let's try one more for today, and then I think we'll be done. Does it still work with fractions? Can I put together some roots if they're fractions?
Yes.
Can I put together these roots? What do you think?
Yes.
They're both square. Okay, so if I put them together, I'm just going to have the square root of 3 over x times y over 2. When you're multiplying those fractions, you would check for anything that you can simplify. Can I simplify anything in this expression?
No.
So we're going to have just a square root of 3y over 2x. That's as far as we can go. Raise your hand if you feel okay with this so far, what we talked about. All right, next time we'll talk about the quotient rule. I'll show you how to simplify radicals in general. That'll be a good day. Well, I guess it'll be on Wednesday. So, last time we were talking about the product rule for radicals, and we said that no matter what our root is, if we have the product as a radicand, we can split up that root as a product of 2 roots, for any nth root. So it doesn't really matter. Square roots, cube roots, fourth roots, anything. What we're going to talk about today is the quotient rule, and then how to apply these things to any radical, and we're going to be able to simplify them. So, the quotient rule says something very similar to this product rule. It says if instead of a product you have a quotient inside of any nth root, similar to our product rule, we can break that thing up. We can do nth root of the numerator over nth root of the denominator. And that's legal too. So products and quotients we can both break up. For example, if you have something like this, a square root or any other type of root for that matter, let's say it's a square root this time of 9/25. All this says is as long as we take the root of the numerator and the root of the denominator, both of them, we'll be okay. So here we'd have the square root of 9 over the square root of 25. Let's simplify this expression. How much is square root of 9 over square root of 25? Or say the square root of y over 36. Now, when we do split this up, we could do the square root of y, for sure, and the square root of 36. Now, while we can't simplify the square root of y, we can simplify the square root of 36. So not all the time are you going to be able to simplify both the numerator and denominator, but maybe one of them you can to make this thing a little bit easier. Which one, what are we going to have when we simplify the square root of y over the square root of 36?
Square root of y over 6.
Good, so the square root of y, nothing happens. Square root of square root of 36 gives you 6. So in one case we have a square root, in the other case we don't. That's legal, that's okay. We can have a square root on the top or the bottom, numerator, denominator. This also works with any other type of root that we have. So for instance, if we have, say, a cube root, it's still legal to split those up. I said for any nth root, so it doesn't really matter what our root is as long as we keep the same process. So in the square root of the cube root of 27/64, we just got to make sure we keep that a cube root and don't, misinterpret that as a square root. So we can't lose that little 3 as our index. How about the cube root of 27? What do we have?
3/4.
So we get 3 for the 27 and the cube root of 64? Yeah. You getting good at those cube roots yet? I hope so. There's only a few numbers you can take the cube root of through 125. Let's practice one more and then we'll learn how to simplify this in any context. Let's practice with a fifth root of 7 over 32x to the fifth. First thing we know is that any type of root we can separate a quotient. That's the quotient rule for us. So we're going to have a fifth root of 7. We're also going to have a fifth root of 32x to the fifth. Ladies and gentlemen, can you simplify the fifth root of 7?
No.
No, I can't think of any number multiplied by itself that gives you 7. You can do it 5 times, it doesn't really work. Now the fifth root of 32x to the fifth, that's something we should be able to simplify. Let's think of the 32, everyone just do this in your head real quick. The fifth root of 32, what number times itself 5 times gives you 32? Do you know it? 2 works, very good. So while I'm not able to simplify the fifth root of 7, the fifth root of 32x to the fifth, I'm going to start off with a 2. How about that x to the fifth? Can you simplify a fifth root of x to the fifth?
Yep.
How much does that give you?
X.
Why x?
Pull out
how does it cancel out? What are we doing when we're canceling out?
Put X in parentheses and fit power on the outside.
Same power and the same root. So as long as we have the same power and the same root, we've got it. I think you were both saying the same thing about the power and the root being the same. Is there anything else that we can do on that problem? We're done. That's as far as we can go as far as simplifying our radicals. How many people feel okay with the product rule and the quotient rule at this point? Good. This row, you guys okay with it so far? Okay. Now, when we simplify radicals in general, we're going to be using a combination of these two rules. We'll be using the product rule and the quotient rule. So this really, it's our bread and butter for this particular section. We're going to be using this almost constantly in combination with the idea of this one. Remember how I showed you two ways to do that, as a matter of fact? A long time ago, I previewed this information. We're going to be using the second way to simplify those roots. All right, here's our goal ultimately. The goal for simplifying radicals, which we're going to do right now, what we're going to be doing is looking for perfect nth roots. So it depends on what type of root you have to what you're looking for inside of your radicand. So if we have a square root, we're going to be looking for perfect squares. If we have a cube root, we're going to look for perfect cubes. If we have a fourth root, we're looking for perfect fourth powers. So what we're looking for when we're simplifying our radicals are perfect nth roots. I misspoke there. Perfect nth numbers, like square numbers or cube numbers. Let's do a couple basic examples. We're going to start off with just some numbers, just practicing simplifying these things. So let's go ahead and do this. Remember this process, I asked you some square roots. You guys were pretty good at that. Square root of 64 is, hopefully not. Square root of 81. Square root of 25. Square root of 144. Of 196. Square root, yeah, 14. Square root of 169 is 13. Square root of 196, you reverse those, 14. That's kind of cool, right? Square root of 225? Just go one higher. 15, very good, all right. Well, we got the hang of this, right? 14.7, I don't know what it is. No, it's 15. Square root of 36. Okay, that's 6. Now, when we say the square root of 18, can you do that?
No.
You can't give a whole number answer for it. However, using this idea, we're going to be able to simplify it to make it at least a little bit smaller inside of our radical. That's the goal. I'm sorry, what type of root do we have here?
Square root.
If we have a square root, here's our goal, ladies and gentlemen. We're going to be looking for perfect nth numbers. So if I have a square root, I'm going to be looking for perfect square numbers. Here's how you think of this, and you've done this before. It's just that this should be a little bit of review here. You just haven't dealt with the variable portion, which I'm going to add on in just a bit. If you have a square root of 18, we need to look for a perfect square number, which you guys just listed out for me when we were just talking about this 30 seconds ago, that divides 18. So for instance, can you think of a number that you can take the square root of that divides 18?
92.
9 works. You can take the square root of 9, right? Do I want 6 and 3? Why wouldn't 6 and 3 work? Because a lot of people go, oh yeah, just find two numbers and multiply. Can you take the square root of 6? Can you take the square root of 3? Then why would you use those numbers? What we're doing is using numbers that you can take, at least one of them, you can take the square root of. Probably only one of them you can take the square root of, otherwise you can just take the square root of the number at the beginning. Because we're going to be using this one of these things. And we need to be able to take the square root or that type of root of one of those numbers. So if we're dealing with a square root, we're looking for a number that you can take the perfect square of, that's a perfect square number, that divides 18, because we're going to split that up. So instead of 18, you told me 9 times 2. So I'm going to write this, I'm going to write the number I can take the square root of first. 9 times 2. You agree that's 18, right?
Yep.
Okay. You see, now that we have this, a product, we can use the product rule, which says if you have a product of a number inside of a radical, I can split that up as 2 different radicals being multiplied together. So instead of square root of 9 times 2, this says I can do the square root of 9 times the square root of 2. Do you see that that's legal? Math legal. Yeah, don't get thrown in math jail for doing that, that's fine. Can you take the square root of 2? Can you do that? Square root of 2 is, I don't know, 1.41 something forever. I don't know exactly what it is. Can you take the square root of 9?
Yes.
Well, that's great, because this at least lets us simplify part of our radical. So, if you can take the square, what's the square root of 9?
3.
This is 3. This was, we can't change that at all. That stays there. So here's the idea. You have the square root of 18 over here, which is some number. We're going to break that number up into a perfect square times something else. We split that up as 2 different roots. And then hopefully, if you've done this right, you'll be able to take the root of one of them. If we can take the square root of 9, that's 3. This is a multiplication, that's a multiplication. The square root of 2, I couldn't do anything with that, so it just stays there. So instead of the square root of 18, I have 3 root 2. Is this a little bit easier to deal with? Yeah, in a math problem it will be. It's a smaller number inside of a radical, that's kind of nice. Plus, in order to add and subtract radicals, which we're going to do in the next section, you have to have them in the simplest form. That's in the simplest form. I think we'll feel okay with this so far. Okay, we're going to try some more examples here before we add some variables in there. Okay, I want you to think on it. Don't say it out loud right now. Think on it. First thing you got to do is think of the type of root we have. What type of root do we have?
Square.
Square root. So you're looking for a perfect square number that divides 98. Don't say it out loud. I want people thinking on this, okay? Think on a number that divides 98. Now, you only have a few numbers to choose from, right? I hope you realize that. You only have the numbers that you can actually take a square root of to choose from. Those numbers are 1, so I can help you, 4, 9, 16, 25, 36, 49, 64, 81, 96, 100, 144, 121, and so on. So can you think of any of those numbers that divide 98?
49.
49 works. Yeah, 49 times what?
2.
By the way, they're not all times 2. That's just a coincidence. Okay. So this would be the square root of, yeah, sure, 49 times 2. Why did we choose 49? Can you tell me why we choose? Why did we choose 49?
We have square root of 49.
Yeah, you can. You can take the square root of 49. That's why we're choosing it. When we do this, this lets us split it up. Square root of 49, of course that's 7. Square root of 2, I can't do anything with that, so we get 7 root 2. It's pronounced 7 root 2, or 7 square root of 2. If we had a third power, it would be 7 cube 2, cube root of 2, or fourth root of 2. So we just say the number and then the root. It's implied that those things are multiplied right there. You ready to move on? Let's talk about the square root of 32. Now clearly we have a square root. We've got a square root. We're thinking of a number that goes into 32 that you can take a square root of that's a perfect square. What do you think?
16.
I heard 16, that's great. What about 4? 4 works, right? However, if you chose 4, I want you to notice something. If you did 4, you would get 2 root 8. Are you seeing that? You can do that quickly in your head. You get 2 root 8. Does a perfect square divide 8?
Yeah.
4 divides it again, you'd have to do the process over, all right? So unless you take the biggest perfect square that divides a number, you're gonna have to do it again. 2 root 8 is not good enough for this. You can't do this and get 2 root 8. Because this you could break up as 2 times 4 times 2. That's 2 times root 2 times root 2. 2 times root 4 times root 2. That's 2 times 2 root 2. You should be getting 4 root 2. That's the final answer that you should have. And the way we can see that is take the biggest perfect square that divides that. In this case, it's 16. Square root of 16 times 2. Square root of 16 times square root of 2, you're going to get 4 root. I promise they're not all 2s. I promise. Okay? They don't all end in root 2. A lot of times, but not always. That's what we should get. This is a lot quicker, a lot more concise. So instead of just immediately going with your first instinct, maybe it was 4 on this case, think bigger, see if you can find the biggest perfect square. You seeing the point there? Yes, no? Okay, get the biggest perfect square. Here, if we just chose 4, it'd be 4 times 8. Square root of 4 is 2 root 8. Then you'd have to do the root 8 all over again. That'd be 2 problems, and we don't want to make that. Not more work, less work. Square root of 14. Square root of 14. Okay, so we'd write this as 7 times 2. Sure. What's the square root of 7?
There is none.
What's the square root of 2?
Which is none.
Well, there is one. It's a decimal. It's not a whole number. Is this going to help you break it up? Okay, so sometimes you're going to get those numbers that you can't simplify them. In this case, you can't simplify the square root of 14 anywhere, but this is why I showed this example to show you the difference between these. It's not just that you're looking for factors, ladies and gentlemen, because I have a lot of people who, they really don't get this process. They think they do, because they can follow it. They go, how do you get those magic numbers? Let me try. And they do 7 and 2, right? And they go, oh, square root of 7, square root of 2, you get 7 root 2. A lot of people give me 7 root 2 on that. Can you take the square root of 7?
No.
Can you take the square root of 2?
No.
Then it's not simplifiable, all right? That's why we're choosing numbers like 16. That's why we're choosing numbers like 9 and 49, because you can take the square root of those numbers. 7 and 2, it's not happening. So we're looking for specific specific factors, factors that you can take the square root of, or the nth root of.
So if you got like a square root of 14, you just say non-factorable.
It would just stay the square root of 14.
All right.
Can we go 14 times 1?
Sure, but the square root of 1 just gives you 1 over and over again. So it's actually not breaking that down any, right? I mean, square root of 14, you'd stay square root of 14, square root of 1 is 1, you'd still get the square root of 14 back again. That's a good point, but yeah, we're looking for numbers besides 1. 1's not going to help us. Ooh. Should we be looking for perfect squares anymore? What do you think?
No.
For instance, the number 4. Is 4 going to help us in this case? 4 times 10.
No.
Can you take the cube root of 4? Cube root of 10? No. So the numbers you're looking for change depending on what type of root you have. Here we have a cube root. We're not looking for perfect squares anymore. We should be looking for perfect cube numbers. Can you think of a number that you can take a cube root of that goes into 40? Now, the numbers you can take a cube root of, if you want to practice these, it's 1. 1 doesn't help us. The next one would be
8.
not 3. The cube root of 3 is not 1.
8.
What now?
8.
8. Because 2 times 2 times 2 gives you 8. Does that make sense? What's the next one?
27.
16.
Good. 3 times 3 times... 16 would be a perfect square number.
Oh.
2 times 2 times 2 gives you 8, right? 3 times 3 times 3 gives you... Then clearly that's the next number you can take a cube root of. Someone else give me the next perfect cube. 64, sure. 4 times 4 times 4 gives you 64. Are you seeing how I'm getting those numbers? I'm taking sequential integers and multiplying them by themselves 3 times. Those are the only numbers you're going to be able to take a perfect cube root of. So 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. So those numbers, those 1, 2, 3, those 4 numbers are the only numbers you should be looking at, unless it's like a really big number, that you're supposed to take as factors for a perfect cube. 8, 27, 64, 125. Do any of those 4 numbers divide this one?
8
No.
and 5.
8 does. Sure, 8 works.
Oh, never mind.
8 times, what was it?
2.
Well, 8 times 5 gives us 40. So if we have a cube root of 8 times 5, we can still split that up. Cube root of 8 times a cube root of 5. Just don't lose that 3. Don't lose that cube root. This is a cube root. It will stay a cube root throughout the whole problem. Ladies and gentlemen, what's a cube root of 5?
You can't get it unless you want to use a calculator.
Okay, on the right-hand side, what's a cube root of 2?
Give it away.
Did. Cube root of 8 is 2. So while we can simplify this, we get 2. We cannot simplify the cube root of 5. We get, well, cube root of 5. Very similar to this idea, only now you're not looking for squares, you're looking for cubes. Nod your head if you're okay with this so far. Okay, good. Do one more. Okay, don't say it out loud. I want you to think on this. I want you to think about it. Firstly, I want you to think about what type of numbers you should be looking for. Should we be looking for perfect squares or perfect cubes? What do you think?
Perfect cubes.
Sure, perfect cube. So think in your head about a perfect cube that divides 54, just in your head. Again, the perfect cube numbers are 8, 27, 64. That's it. It's the only 3 you have to choose from here. By the way, is 9 going to work? Should you be putting 9?
No, that's.
Can you take the cube root of 9? No. You take the square root. If that was a square, that'd be great. But it's not. So, does 8 go into that number?
Nope.
No. How about 64? Definitely not. It's way too big. The only other one we have to choose from is 27. 27 goes into that 2 times. We'll write the number we can take a cube root of first. Again, we can split it up just like we did the previous examples. We'll have the cube root of 27 times the cube root of 2. Cube root of 2, we're done with that. We can't simplify it anymore, but the cube root of 27 gives us how much, everybody? That wasn't everybody. You got lazy today. Come on.
3.
Play along. Have fun. Yeah, this gives us 3. Then we have a cube root of 2. That's as simple as we can make it. Cube root of 54 gives us 3, cube root 2. Would you raise your hand, feel okay with this so far? That row? Yes, no? Okay, good. Very good. Can we do the same thing if we have variables? Do you need this anymore?
No.
It should be tattooed on your brain at this point, right? For some of you, learning math feels like getting a tattoo on the brain, doesn't it? Have you ever had a tattoo before? They kind of hurt, so that's what the analogy was for. Oh, anyway. Whatever. Oh my, square root, not a cube root anymore, square root of 81y to the 5th. Square root of 81y to the 5th. Now, we're going to be looking for perfect what roots? Perfect squares, perfect square numbers. 81, we got that. Square root of 81 is what? Now, the square root of y to the 5th, now that's the problem. You see, in the previous sections that we did, specifically 10.1, I told you that sometimes we're able to simplify powers of variables by taking that number to a certain power and crossing out that power. Remember that? But then I said, this isn't always going to work. Because is there any way that we can make y to the 5th as something to the 2nd power?
No.
Not unless you want to do 2.5, and that really would not be good for us. Okay, we can't do that. So no, there's really not. So we had to have a different method. And when I said there's another way that you could do this is to split up y to the 5th as many y squareds as you could. Here's the point. What we're trying to look for is, I'm sorry, perfect what's here?
Squares.
Squares. So powers of 2. Here's the point. If I have x to the fifth, like I have y to the fifth here, I can write this a lot of different ways. I could choose to write this as, that's true, isn't it? Sure. Or this one. That's true, right? Or I could do that one. That's true. Or I could do this. Is that still x to the fifth?
Yep.
Now what we're trying to do is write this with as many power 2's as we can. Would you agree that this way is giving us as many power 2's as I can?
Yeah.
Here I don't have any. Here I have one. That's great. But this one, that's not so good. This one doesn't give me any power 2's. That's not good at all. This is the most power 2's I can find. Now, why I'm looking for power 2's, and I showed you this earlier as just a review at this point, is whenever we have a power 2 matching with a square root, or whenever the power matches the root, I can take out one of those x's outside of my radical. It simplifies. A square root and a square root undo each other. So since I have a square root, I'm looking for x to the power 2 in this case. I hope you remember that we've done this already at least a couple times. I'll keep this square root of 81 because I don't need to break that number up anymore, such as 18 or 98. That's already a perfect square, so I don't need to split that up. If you take the square root of it, leave it alone. But y to the fifth, instead of leaving it y to the fifth, I'm going to write this as y squared times y y. As many y squared as I can, but I still need y to the fifth. So I can't just leave it y squared times y squared because that's y to the fourth, I need y to the fifth. Raise your hand if you're okay on this so far. Good, all right, that's good. Now let's see what happens here. Can you tell me what's the square root of 81?
9.
So I'm going to cross that out and put a 9 because I just took the square root of it. That means I pull it outside of my radical. Are you following me here? Okay. Can you tell me what's the square root of y squared? Remember what we could do, why this whole process works. I'll show this to you here. Because of our product property, you could do the square root of 81 times the square root of y squared times the square root of y squared times the square root of y. Do you see that that's the same thing we're doing right here? Not sure if you're with me. You have to kind of get this part. Are you okay that what I just did is what we did here, what we did here, what we did there? Yes, no? I can split that up by the product rule because any nth root I can do that. So square root of 81, square root of y squared, square root of y squared, square root of y. Why am I choosing the y squared here instead of like y to the third or y to the fourth? Well, it's because I can take a square root with a square and cross it out and simplify it. Now we can say, okay, what's the square root of 81? Oh, that's 9. What's the square root of y squared, folks?
Y.
Good. Because we know those simplify. What's the square root of y squared?
1.
What's the square root of y?
Stays square root.
Can I do it? Can I simplify it at all?
Nope.
I'll give you actually a big hint. If the power is bigger than or equal to the root, you can simplify it. If the power is less than the root, you can't. Why?
You can't break it down anymore.
You can't break it down anymore, that's right. If the power is less than the root, that's power 1, I can't write that as a power 2 times something, right? If it's equal to it, I can simplify it. If it's greater than it, I can write it as a product of those powers put together. Does that make sense? So if it's bigger than the root, simplify it. Or equal to the root, simplify it. If it's less than, you're done. You can't simplify that. So in our case here, we cannot simplify the square root of y. I'm just going to leave that square root of y. Now can I write this any simpler than this?
9y squared.
Sure, yeah, let's put those y's together. Really don't need these because if I write it like this, it's implied that we do have multiplication. That's as good as I can make it. That's completely simplified. You okay?
Yep.
Can you get directly from here to here without showing this step? Sure, you can do that. Or actually here to here, here to here. Point right correctly. This one to this one. Sure, you could. You could do 9. This gives you a y outside of your radical. This gives you a y outside of your radical. But this one, you wouldn't be able to cross that out, would you? Doesn't match. Stays inside your radical. That's the way you do this. Let's try a few more here. See, we're having fun now, right? Don't we love? I loved crossing things out when I was your age.
Or so.
Although maybe I'm not some of your age yet.
I'm like older than you.
That'd be awesome. See, when I taught high school, I was always the oldest one in the room. It sucked. I felt they all thought I was 50.
Oh.
Yeah, they did. I was 24 at the time when I started teaching high school. They're like, "You're old, huh?" Do I look I got brothers like as old as you. It's the ones who actually had brothers and sisters of my age were like, "Okay, yeah, I know how old he is." But some were like, "What are you, like 40?" 40. They failed. They failed.
And that's why you started teaching college.
No comment. No comment. Okay, cube root 24, a to the 9th, b to the 4th. What we need to do is write this as perfect, whatever type of numbers we need to simplify this. So what type of root do we have? We're looking for perfect cube numbers then. The thing we deal with is the number itself, and take some time to actually write this out. Okay, don't do all of this in your head. I don't want you making mistakes right now. Write this out because we're just learning it. Okay, don't take shortcuts now. So since we have a cube root, we're looking for perfect cube numbers. I want you to all think of a number, perfect cube, look at the 24, that divides 24. What is it? What is it? It's got to be a perfect cube. It's got to be a perfect cube. A number that you can think of that says, I can take a cube root of that number. So while we can do 12 and 2, can you take the cube root of 12?
No.
Cube root of 2? No. So don't pick those numbers. Pick different numbers. What number can you take the cube root of that divides 24?
8.
So pick 8. 8 times 3 actually gives you 24. Why did I pick 8? I can take the cube root of 8. That's why I picked 8. The 1, 2, 6, and 4 can't take the cube root of those numbers. Are you starting to see what number? Why I'm picking the numbers I'm picking? I'm sorry. Now, a to the 9th, we now work on our variables. A to the 9th, we're going to write this as many powers of a to the, what power? Are we looking for squares? Should I write a squared times a squared times a squared times a squared? Should I do that?
No, it's cubes.
Why cubes? Yeah, sure, cube roots, okay. So I want, tell me how many I need. A to the, times what? Times? Anything else? Is this still a to the 9th? Why we pick the third powers again is because everywhere we have a to the third power, we're going to be able to cross it out, take an a outside of a radical. How about b to the 4th? B to the 4th. What do I want to write that as? You have choices, right? You can do b squared times b squared. Is that a good choice for you here? No, we want what?
B to the times.
Cool. Now, everywhere we match the power with the root, we cross it out. Everywhere that we don't, that stays inside of a radical. Here's the reason why, again, I'll show you this step one more time. This gets annoying though. So we're going to, ultimately, we're going to skip this step because this kind of sucks. I don't want to have to write this every single time because you'd write the cube root of 8 times the cube root of 3 times the cube root of a cubed times the cube root of a cubed. Forgot my 3's. Cube root of a cubed times the cube root of b to the 3rd times the cube root of b. It works because you can do this. Because you can split that up. Do you see where these numbers are coming from, first of all? I'm just splitting this up. 1, 2, 3, 4, 5, 6, 7. Okay, 7, I got it. So we're just splitting that up. But everywhere you see, you can simplify this one, and this one, and this one, and this one, and this one, but not these two. Do you guys see what I'm talking about here? So while we could do a 2 here, you can't do anything with this one. While you can do an A here, and an A here, and an A here, that looks like a 9, and a B here, you can't do anything with this one. Nod your head if you're okay on that step. This row, you guys all right with that?
No, you got the 2 again? 3.
Cube root of 8 is 2. So now you'd have to simplify all this stuff. Put the roots back under one root. Put your variables that are being multiplied together as powers. So we'll have a 2, we'll have an a to the third, we'll have a b. Can you tell me what goes inside of my cube root?
3b.
Got the 3 still, got the b still.
That's your
That's as good as we can make it. You can't simplify 3. Please don't do this. Please don't go, oh, cube root of 3, that's a 1. Okay, we don't do that. Right, the only numbers you can take a cube root of are 1, 8, 27, and 64, and then 125. That's it. That's it. How many people feel okay getting from, I'm going to have you raise your hand here, getting from here to here, raise your hand. Okay, that's probably the most important step. From here to here, actually knowing what to split up. How many people feel okay getting from here to here? And then from here to here, that's an important one as well. Feel all right with this? Okay, good. That's fantastic. Let's try one more together. We'll give you a couple to do on your own. Then we'll talk about the last thing, how to do this with some quotients. Not any harder. In fact, sometimes it makes things a little easier. You just have to be very careful and do exactly what I tell you when we get there, okay? So I'm pre-warning you, you got to do this exactly like I show you. Otherwise, you're going to make mistakes on your test, I guarantee it. And I want to set you up for success. It is cool. Okay, there we go. Fourth root, 32, x to the 7th. I just said fourth root. So, really shouldn't be looking for square roots. Shouldn't be looking for perfect squares. Shouldn't be looking for perfect cubes. Should be looking for perfect fourth powers. Perfect fourth powers. Okay. So, the first thing we deal with is 32. Just think in your head, think of a number that you can take a fourth root of that divides 32. Now, if you're having a hard time dealing with this, start taking the integers and multiplying them by themselves 4 times. Those give you the numbers you can take a fourth root of. So, for instance, the first one is, don't start with 1. 1 times it itself is just going to be 1, okay? Start with 2. 2 times 2 times 2 times 2 gives you how much?
16.
Does 16 go into that number?
Yep.
Yes.
Just take it. 3 times 3 times 3 times 3 is already 81. That's way too big. Okay, so when we're looking at numbers to the fourth power, 2 and 3, that already gives you 16 and 81. 16 goes into this stuff. So I'm going to write this as the fourth root of 16 times, 16 times what for 32, ladies and gentlemen?
2.
Okay, and then, x to the 7th. I need to be really good at breaking up x to the 7th. X to the 7th, I should write this as what times what?
You said 4 times x.
Good. We want the fourth because we know we can split that up. We can take the fourth root of x to the 4th and get x. So I don't want x squared, so I don't want x to the 3rds. I'm going to get an x to the 3rd by coincidence, but I'm not looking for that one. Do you understand why I'm taking x to the 4th power here, folks?
Yep.
Okay. Now, I'm going to omit this step. I'm going to go directly to the next one. So let's see, I want to show you how that's done here, all right? Firstly, you're going to cross out the things, the items, the factors that you can simplify. So for instance, the fourth root of 16, how much is the fourth root of 16?
2.
So we're going to cross this out and we're going to put a 2. Because the fourth root of 16 is 2. It's just like splitting this up. We're just doing that in our head. What's the fourth root of 2? Can you do that?
No.
You're going to circle it. Whatever you circle stays inside your radical. What's the fourth root of x to the 4th? Yeah, the power matches the root. That's why we picked it. That's why we did that. Cross it out, put your x. What's the fourth root of x to the 3rd? Can you simplify it? Do you notice how the power is less than the root? It stays. Circle it. Once you've circled, you write it back inside your root. Everything else you've already taken care of. So we still have a root of 2x cubed. Now I've made a very common mistake here on purpose to show you something. What mistake have I made? I've made a mistake.
You crossed out the other half.
I didn't mistakenly cross out anything. I crossed out everything perfect.
You forgot 4.
Okay, this happens all the time. People will get this perfect, they'll get this perfect, and they'll make a mistake, and I have to mark off 2 points for this mistake. What mistake was it?
That's a little 4.
Yeah, that you just changed this from a fourth root to a square root. Is that good? No, you won't do that. Square root, you'd still be able to simplify that, wouldn't you? This is a fourth root, though. Now you're done. Okay, so don't lose the type of root that you have. Try 2 of these examples on your own. Then I'll show you how to work with some quotients, and we'll be done. Okay, we're going to start on the first one up here. Square root of 36z to the 7th. First thing I need to do is write this as many perfect squares as I can. 36 is already a perfect square. That's nice. So 36. However, z to the 7th, I'm going to write this as z squared, another z squared, and z. This is what some of you feel like doing in my class, right? Get it? As a joke. It's very funny. So when we do our square roots of 36 and z squared and such on, we get a 6, a z, a z, a z, but this one stays inside of our square root. So our final answer here is 6z to the 3rd square root of z. I need to know how many people got it. Good for you, okay. That's good. You see why this works. Z to the 7th, z squared, z squared, z squared, z. That adds up to z to the 7th. You're matching up the power with the root. So square roots and square numbers. Next up, cube root. Cube root of 32, x to the 4th, y to the 7th. Now we can't take a cube root of 32. That's not a perfect cube number. But we are going to think of a number that you can take the cube root of that goes into 32. Did you find that number? I hope so. Did you? How many people found it? Well, that's about half of you. Oh, that's more than half of you. Okay, you were just lazy and raising your hand. I see. Wow. So 32, we're going to write this as, instead of 32, some perfect cube, that's 8, times whatever else it takes, that's 4. You need to write that as 8 times 4. The reason why, you take the cube root of 8. You can't take the cube root of 4, it's going to stay inside of a radical, but you can take the cube root of 8. Now, x to the 4th, can you please tell me how I am going to write x to the 4th power, please? Good, okay. As many x cubes as I can, because I know power root, that's what we want, times whatever else it takes to match up to x to the 4th, or to add up, because we're adding exponents. Now, y to the 7th, same idea. Y to the 3rd, y to the 3rd, y. This is still y to the 7th. I'm just taking as many y to the third powers out of that as I can. Did you make it that far? Okay, now we get to cross stuff out. That's the best part. We get to simplify. The cube root of 8, that gives you 2. Cube root of 4, can I cross that out? That stays. Cube root of x cubed, great, that's x. Cube root of x, can I cross that out?
No.
That stays. Cube root of y cubed, y. Cube root of y cubed, y. Cube root of y, no. Only the y cubes because those match up. So whatever I circle stays inside of my radical. I'm going to simplify this stuff. 2xy squared, cube root of 4y. That is as far as we can make it. Don't forget about your cube root of the inside stuff. What did I do? Oh, I forgot about the inside stuff. Ironic. You know what happened? These glasses have that thing right there, and I couldn't see it. It's just like that. I saw the 4, and that's weird. Darn eyes, not seeing stuff. Ever. Now, we're probably not going to be able to make it through all 3 of these in the last minute and 48 seconds, but we're going to try at least a couple. Here's the biggest point I can make about this. Before you do these problems, you absolutely have to use the quotient rule to combine them. First 2, you could do them without it. But it's gonna be very hard to do this last one unless you do what I'm telling you right now. You have to combine those roots first before you simplify. Write that down. Write combine roots first before you simplify. Combine first. Why? It makes things easier. Oh my gosh. If you do this, look at this. I want you to look at this problem for me before we're going to do a couple of those. But on this problem, if you try to, you can simplify that, sure. You can simplify this one. That negative's going to probably throw you for a loop. You're like, what the heck? But then you're going to have to combine them anyway and simplify again. That's going to suck. So instead of simplifying, then combining, then simplifying, that's 4 steps. You can do this in 2 steps. You combine, then you simplify all at once. Isn't that better? That's better. Combine them first. Here's what I'm talking about. You're going to see this. I could simplify that. That's going to be 5 root 3. The root 3's would cross out. However, if I consider the quotient rule says this is the same thing, powers match up, as 75 over 3. True? I can take 2 roots that are being divided, make them 1 root inside of a radical. What is 75 divided by 3?
25.
Can you take the square root of 25?
5.
That's way easier than simplifying here, doing that whole process, and then ultimately finding the square root. Are you with me on that? Okay. Last thing I got to show you today, we're going to do this problem, then we'll be done. What to do with that 3. Is this 3 on the numerator or denominator of our problem here? Then it's got to stay on the denominator. This 3, it's not inside of a root. Here's what this means. This means 1/3 times the square root of 80y over the square root of 5. That's what that means. Notice how the 3 would be on the denominator of that problem. Nudge if you're okay with that. Yes, no? So what you're going to do, leave that 1/3 out front. Don't even worry about it till the end of your problem. You can't forget about it, but don't even worry about it. Break that 3 off. It's not part of your root. It's just being multiplied 1/3 times this. Denominator, denominator, denominator. Then combine your roots. So you'll have 1/3 times the square root. Since they're square root over square root, I can do 80y over 5. What is 80 divided by 5? How much is it? Is it? So instead of 80y over 5, you're just going to put 16y. That's nice, right? 80 divided by 5 is 16. So we have that. Can you take the square root of 16? Can you take the square root of y? Are you going to be able to simplify that? That's a power 1, that's a root 2. So the only thing we'd be able to do is do 1/3 times the square root of 16, remember you're multiplying here, is 4. I can't simplify the square root of y. Get that. How many will feel okay with this so far? What you can do with 1/3 times 4, 1/3 times 4 is like 1/3 times 4 over 1. You get 4/3 square root of y. Or 4 root y over 3. You just put that 3 right back on the bottom. That's an appropriate answer. You're completely done with that. Raise your hand if this made sense to you today. Good, all right. We'll work on a couple more of these next time. We'll do 2 next time, and then we'll do 1 on your own and be good. So last time we were still talking about these radical expressions, and what we realized is that in order to combine or simplify these radical expressions, the first thing you have to do is combine them. I told you that really what we really never want to do. We never want to simplify the numerator, simplify the denominator, and then combine them because you're going to have to re-simplify it all over again. So I think last time, the last couple examples were combine those radicals first using the quotient rule, and then simplify them. Do you guys remember that from yesterday? So when we look at this problem, firstly, can you combine them? Yeah, what tells you you can combine them?
The cube root.
Good, they're both cube roots. And the quotient rule said if you have the same type of root, you can put them under the same fraction, under the same radical. Have one fraction under that radical. Do you remember that? Okay. Also that 5, is that 5 inside the cube root?
No.
That 5, what it means, just like the 3 did on one of our previous examples, this means 5 times something. So what we're going to do with our problem here, before we even start it, we're going to take this 5, since it is being multiplied here, we're just going to kind of pull it off to the side and hold it there to the end of our problem. Now, is the 5 on the numerator or the denominator?
Numerator.
What that means is that this is going to be on the numerator for the whole entire problem. Are you with me on that? So it's not going to move to a denominator or anything. The 3 last time on that example, if you remember from yesterday, that was on the denominator, that stayed on the denominator, and at the very end we had something over 3. Here we're going to have 5 over something. That's our whole idea. So what I'm going to do is, this is very much like 5 times, 5 over 1 if you want, 5 over 1, it's on the numerator. Five times this radical expression. Now, what tells you that you can combine those radicals is that you have the same exact type of root on both the numerator and denominator. If you ever have that, if you ever see this, and you're talking about simplifying radicals, the first thing you need to do, make one radical out of it. Please, please, do not simplify this one first and try to simplify this. You can't even simplify that one. Did you guys see that? Power is less than the root. That 3 is not a perfect cube. You can't even simplify that. So at some point you would have to combine them anyway. Do it first, that way you don't waste your time. Up here, you'd simplify this, then you'd combine them, then you'd have to simplify anyway. That would be a tremendous waste of time. And it's hard to do that when I throw negative exponents at you too, which I'm going to do in just a little bit. Okay, so very first thing we're going to do, we're going to leave this 5 alone, 5 times, and we're going to make this one radical. We're still going to have a cube root, that doesn't change, but inside of our cube root, we're going to have 162x to the 8th over 3x squared. Now just if you're okay with that one. Just a little step, right? Just a little step. Make that one root first. Why?
And now you can simplify.
You can, right? Can you simplify 162 over 3?
Yep.
Yeah.
Do it on a calculator if you haven't already. How much is 162 over 3? How much?
54.
54, okay. Can you simplify x to the 8th over x squared?
Yeah.
Sure, hey, exponent rules. That's why we covered those. So if you're looking at this problem, well, I know this 5, I'm leaving it out there. But under my cube root now, without doing any radical simplification, we're able to make this fraction a whole lot better. I know that 162 over 3 is, you guys said 54. Can you tell me, how much is x to the 8th over x squared? What do you do with those exponents?
Subtract.
And so we're going to get x to the...
6.
Perfect. Remember that? Subtract exponents. Now I want you to look at this thing. Can you simplify that?
Yep.
Is it easier to simplify than this? It's even easier. That's even better. This is what we want to deal with. So I'm going to make a real strong point here. You must combine before you simplify it. I'm going to give you a problem very much like this on the test. The people who simplify first probably aren't going to get it right. The people who combine them first, you're definitely going to get it right. combine it first, then simplify, no big deal. The one I'm going to give you on your test is actually going to have some negative exponents on there. And so you're going to have to know how to deal with that. So make sure you're combining first before you're simplifying. Let's go ahead and finish this off the rest of the way. I'm going to leave that 5 out there still. It's just going to be hanging out 5 times. And then the cube root of 54x to the 6. I haven't lost my cube root the whole way through. You can't lose your cube root. We're going to look for 54. Can you think of a perfect cube that divides 54?
27 and 2.
What was that? 4 is not a perfect cube.
27.
27, sure, that's a perfect cube. So we're looking for those perfect cubes. So remember, on this case, we're not looking for numbers like 9. We're not looking for numbers like 16 or 4. We're looking for perfect cube numbers, which would be 8 or 27 or 64. Now there's only 2 that we have a choice of because 64 is already too big. The only ones you can choose from are 8 and 27. So you need to know what type of root we're dealing with. If it's a cube root, we're looking for perfect cubes. 8's not going to work. 8 doesn't go into 54, but 27 does. Remember 27 as a perfect cube? We did a cube root of that. So 54, I'm going to write the 27 first, times, what is that, 2? And the x to the 6th. I can deal with x to the 6th. How am I going to split up x to the 6th in this particular case?
Times x squared to the 3rd power.
I could do that, or,
X squared.
yeah. We break off as many x cubes as we can. Why are we choosing x cubed in this case?
It's a cube root.
Yeah, we know that everywhere we see a power 3 with a cube root, we're going to be able to cross that out and take x out of our radical. Let's go ahead and do that. I want you to notice that I haven't lost the 5. The 5's still up out here. I haven't done anything with it. That's okay. I've not done a thing with it. You just can't lose it. Don't lose your 5. And don't lose that little 3. Don't lose your index. So we've got the 5 still hanging out. At this point, though, we're going to simplify the rest of our problem. Notice the 5 is right here. What's the cube root of 27? We'll cross out, put a... What's the cube root of 2? Okay, so what am I going to do with that? I circle it, signifying I'm going to leave that in my cube root. Cube root of x cubed gives me how much? Cross it out. That's x goes outside of our radical. This one, oops, I did the wrong thing. This one also gets crossed out. That gives you an x. Whatever's left circled stays inside of the cube root. Raise your hand if you feel okay with this so far. Middle row, are you okay with this? Okay. Can I make this any prettier, any better looking?
Yeah, just combine the outside.
That's 5 times, right? 5 times 3. I can make that into
15x squared.
good. Yeah, that's going to be x squared. I certainly don't want to forget that's a cube root. And there's only a 2 inside. So our answer is 15x squared cube root of 2. Feel okay with this so far? Told you this was fun, huh? Lots of fun. What would you rather be doing on Thursday, honestly? I mean, nothing really. Nothing. Not sleeping. No, you'd rather be dealing with negative exponents, clearly. Clearly.
Friday.
Oh, negative exponents only happens on Friday.
Yes.
I see. Oh my. Oh my. What's different about this problem than the last one?
Negative exponents.
Okay, 4th root, that's one. And then the other one?
Negative exponents.
Yeah, you got negative exponent. Hey, let me tell you something. If you forget what I tell you and you forget to combine these first and you try to simplify the top and simplify the bottom, because that's all I'm going to put on your paper is simplify. And you're going to have to know what to do. So if I put simplify here and you start simplifying this one without combining these first, you're not going to make it. You're not going to make it unless you realize you have to combine them at some point anyway, but it's going to get pretty confusing if you do that because you're going to have a lot of stuff going on up here, and then you're going to try to combine that with the stuff down here, the negative exponents, which you cannot simplify this in any way right now at all. You're going to be very confused on what to do. The goal of this is to simplify. However, whenever you have the same root over the same root and you were trying to simplify, put them together first. You know why? If you looked at the last example, what happened here was whenever we had the common base, we were able to combine them, right? And change two problems into just one problem, which was a little bit easier even. That's the whole idea. So instead of dealing with x to the 9th and x to the negative 3, that's a common base. We are going to be able to combine them. Do you guys see it? You're going to be able to combine them somehow. And that's going to be easier to deal with. So that's the whole purpose here in combining your radicals. So whenever you see those, the same root over the same root, you got to combine them. Now also we've got a 3 up here just like we had the 5. That 3, I'm going to leave it hanging out just like I did the 5 over here. Now is a 3 on the numerator or denominator? Notice how the 5, we left that, it was on the numerator, right? This wasn't 1 over 5, this was 5 over 1 the whole way through. If the 5 had been on the bottom of my fraction, this would be 1/5, and I would be getting this whole thing over 5. Are you with me on that? That would be a 3, and this would be over 5. Let's do the same thing here. So I'm going to start off the same exact way and have a 3 times 4th root of all this junk. Okay, that's the first step. I gave you the first one. Now, can you please tell me the next step? What would I do now? Combine them. Great. What lets you know that you can combine these?
They have the same root square root.
Okay.
Fourth root.
Same type of root, yeah. If that was a 4th root and that was a 3rd root, you couldn't do anything with it, but fortunately they're the same root. So we're going to make this, it's going to look identical. The only difference is this thing is not going to be here. You have one big 4th root. So the 3 is going to stick out front still. Make one big 4th root out of it. One big 4th root. Okay, so on the right-hand side of the room, what do I do now? What now?
It should be 32x to the 12, y to the 5.
So we're going to combine them, sure. And we know exponent rules, so this should not be a big deal here. The big deal is actually the simplification part. I've already taught you how to do this. I've already taught you how to combine these things as well, right? I've already taught you that. That's old stuff. Okay, so we look at the number first. Of course, there's no constant term over here. So we're going to have just a 32. Now, I am going to deal with these problems individually. I had the x's, I had the y's. So I'm going to do those piece by piece. Let's please look at the x's first. We've got x to the 9th over x to the negative 3. Now, you tell me, what do you do when you have common bases being divided? Do you add exponents or subtract exponents?
Subtract, but it's a negative 6
Subtract.
and end up then.
So when we do it, we do have the x to the 9th, and we are going to subtract. But be very careful. What are you subtracting? Are you subtracting 3?
No.
No, because this right here, that will be subtracting 3. That way you would get x to the 6th. You with me?
Yes.
We're actually subtracting negative 3. Now I'm going to draw it a little bigger so you can see it better. This would be subtracting 3. Right now we're not doing that. We're actually subtracting negative 3. That's like adding 3. So when you are dividing by a negative exponent, you actually add that up there. And you can pretty much see this if you really want to think about it this way. If that's a negative exponent, this means it's in the wrong position. It means it actually belongs up here on this fraction. That would change it to x to the 3rd, positive 3. Does that make sense to you? Then when you combine them, you would see you would get x to the 12th. And that's exactly what we're going to get here is x to the 12th. Does that reasoning make sense to you? Okay, so we're not going to get x to the 6th. You're subtracting a negative. That's x to the 12th. Because of that reason. How about the y? Are we going to get y to the 6th still, or y to the what? Okay, that has a little power 1, even though we don't show it. It's got a power 1, so we do the 6 minus 1, that gives you y to the 5th. Now what do you do?
Now you have to break apart the 32 so you can get a 4th root.
Okay. And we got to do, can we simplify these? What do you think? Well, let you know you can simplify these.
They're greater than 4.
Okay, so the power is bigger than that root, we can do that. Do it. Go for it. See if you can simplify the rest of the way. If you finish quickly on that simplification, try this next problem. That's what we'll start with after this. Okay, so we're looking at this one. I'm going to finish this thing off. I'll give you some more time to do this in just a second. Let's go ahead and work on this so you know whether we got it right or wrong. Firstly, with the 3, we're not going to do anything with that 3. We're just going to leave that out front for now. But we are going to try to simplify the inside of our radical right here. Now that 32, we're looking for a perfect fourth power that divides 32. The only perfect fourth power I know that's less than 32 is actually 16. That's 2 times 2 times 2 times 2. That's only one. So unless that goes into it, we're not going to be able to simplify this. 16 fortunately does go into 32. How many times? So 16 is the perfect fourth power we were looking for. 16 times 2 gives us 32, so we're going to be able to split up our 32 like that. Now x to the 12. I'm going to look for as many x's to the power 4 as I can. In this case we have x to the 4th, and we're going to have that 3 times. I'll make sure that I double check to see that that actually adds up, because we're adding those exponents now, since we're multiplying to 12. It does 4, 4, 4, that gives us actually 12. So we know we have the same expression so far. Now the y to the 5th, I can also break that up. The power is greater than the root. That means I can write this as, I'm going to choose to do y to the 4th times y. That's as many y to the 4th as I can, then whatever is left over, that still makes up y to the 5th. Did you write it like that as well? Good deal. Now, we're still going to leave that 3 out there. That 3 hangs out until the very end, until we can multiply it by something. We'll take the 4th root of 16, that gives you 2. 4th root of 2, I can't do anything with that. I'm going to circle it, it's going to stay inside of my radical. 4th root of x to the 4th, that gives you x, then x, then x, another y, but that y I can't do much with. The power is less than the root, that means I can't simplify it anymore. So there's only 2 things left in my radical. Definitely want to make sure I have a 4th root. Make sure that 4 is there. Then I'm going to have a 2y inside of it. I'll clean this up a little bit. I know 3 times 2 is 6. That's why we left that 3 out there. We didn't lose that. This gives you the x to the 3rd, y, and then we want to make sure we do a 4th root of 2y as well. That's as simple as I can make it. That's a lot more concise than this. Looks a lot better than that, doesn't it? That would be a much easier to work with than this and another problem. How many people were able to make it down that far? Good for you. That's good. Okay. Now, I want you to continue working on this one. Notice a couple things about this. Firstly, we have the same type of root or the same type of root. You are going to combine those first. The 5, however, is not on the numerator like the 3 was. It's on the denominator. So keep that on the denominator. If you end up multiplying by 5, if you end up multiplying by 5 at the end, you kind of did something wrong. Right here, the 5 should be on a denominator at the end of your problem. If you do it the same way as this problem, you've done something wrong. Okay? Because right now this 3 was on the top, that's why we multiplied by 3. This 5 is on the bottom. We should have 1 over 5 somewhere. So continue working on that. I'll give you about another minute. about to get going on this thing. As I was saying, the first thing you should notice on this is that 5, now, while it's outside the radical, we are going to have to deal with it at some point. We don't deal with it initially, but we do need to notice that it is on the denominator of a fraction. So when you're going through this problem, sure, take the 5 out. But we can't write it as 5 times something. That's not right. That would move it to the numerator of a fraction. That'd be like 5 over 1. When in fact, what we really have is this is like 1/5 times. That 5 is on the denominator, the 5 is on the denominator. So instead of 5 times, you're going to have 1/5 times. Did you guys do that as well?
Yep.
Okay, so make sure you have that in the appropriate spot. Now the rest of it, that's okay. We're going to break that off, and we're going to combine these radicals. Since I have a cube root and a cube root, I know I can write one large cube root of this fraction as being part of the radicand. We certainly don't want to try to simplify at first, it's way too hard. Make sure we combine them, especially with that negative exponent. Make sure you combine them, that takes care of the negative exponent. There's nothing you can do with it here, but here you can combine those and that negative exponent's gone. Does that make sense for you? That's kind of nice. So we'll leave that 1/5 out front. Again, we're not going to touch it yet. And the cube root we'll be able to simplify. So 40 over 5, that's going to give you 8. X to the 5th over x to the negative 1, you're subtracting exponents. 5 minus negative 1 doesn't give you 4, gives you, good. So you're taking 5 minus negative 1. 5 minus a negative, that's adding. Lastly, we got y to the, now that you do still subtract, you subtract in both cases, but we have 7 minus positive 2, that's going to give you, that's y to the 5th. Show of hands, how many people were able to make it that far? Good, that's the most important step right there. If you can make it that far, you have a much better chance of succeeding in this problem right now. Because this is something we've done before. At this point, we'll try to break this up to simplify this. It's a cube root, so we're looking for perfect cubes. Of course, 8 is already a perfect cube, so I'm going to leave that alone for now. I know the cube root of 8 is 2, so why change that? We don't want to do that. Inside, though, I have x to the 6th. I'm going to write as many x to the 3rd powers as I can. Fortunately for us, that still is x to the 6th. We have 2x cubes. We're not going to have any x's left inside a radical. Y to the 5th, I know I want to break off a y to the 3rd, because that's going to simplify, and I'm left with the y to the 2nd. Still so far so good? All right, cool. Now's the fun part. You get to cross some stuff out. We're still going to leave that 1/5. Cube root of 8 gives you 2. Cube root of x cubed gives you x. Cube root of x cubed gives you x. That's why we did that, because every time the power matches the root, we get to cross it out, take an x outside, or a y outside in this case. And lastly, well, the y squared, the power is less than the root. It's certainly not the same thing, so we can't cross it out. We can't take the y out. We leave it inside of a radical, so we get a cube root of y squared. Did you make it that far? Yeah, no? Good, all right. The last thing you got to do is clean this thing up a little bit. Now, when you do that, I know this is going to be 2x squared y and a cube root of y squared. What do you do with the 5, though? Yeah, it's just going to be on the denominator. 1/5 times any expression says you're going to have that expression over 5. Multiplying by a fraction is the same thing as dividing by its reciprocal. So if I multiply by 1/5, it's the same thing as dividing by 5. So this is the same thing as that. That's a true statement. So if you have the 5 on the denominator, notice 5 was on the denominator the whole entire time. Just stuck on the denominator. We actually didn't even do anything with it. Now if this had been like 10 or 15 or 20 or something, you could simplify that for sure. But at this point, we can't simplify that any more than we just did. Did it make sense that the 5 stuck on the denominator the whole time? Definitely don't want to have 10 right here. You give me 10 right there, that means you multiplied by 5 instead of multiplying by 1 over 5. That's a different expression. Would you raise your hand feel okay with what we just talked about? Might want to try some of those problems. There's several of these on the homework. Make sure you get them right. Check your answers at the back of the book. Make sure you can do them without following your notes all the time. Okay, you need to be able to look at that and be like, oh yeah, I know exactly what to do. Bam, bam, bam. When we get time for the test, that's how well you need to know it. Now, are you ready to move on and start adding and subtracting these things? Booyah! Yeah. I'm excited. I'm excited about it. I don't know you guys. I think I saw some head shakes. No, I'm not ready. I'm not ready. Come on. No, you're ready. You're ready. Trust me, I'm the teacher. I know. I can see it in your eyes. You guys are just, you're sandbagging, right? No?
What?
You never heard the expression sandbagging?
No.
No, am I that old? Oh my God. How many people know what sandbagging means? Okay, you're younger than me, that's good. Sandbagging means that you pretend like you can't get something, that way when it comes time to actually do it, you either don't have to do it or you perform really well at it. So it looks like you're not. So it looks like you just, like we used to sandbag it at weightlifting class all the time. So like when you started out, you're like, oh, this is really hard. And then when it came time for you to actually do it, you just go, and that way you would get full credit for the class because you sandbagged, right? So you didn't actually perform, well, you didn't actually improve. You just looked like you improved at sandbagging. Anyway, you learned something about sandbagging today. That was all about math, wasn't it?